when charges flow through any load in a circuit, we know that they'll encounter some resistance to their flow, something that's trying to sort of block their motion through. And that'll result in them losing some of their electric potential energy. And in fact, that's why it's really important to have loads in our circuits. Because if there is no load at all in a circuit, then the charges would just flow all the way around the circuit, and then they go back to the source and just get more energy from the source. Over time, though, they would just build up more and more energy to the point where it would be too much energy for those conducting wires to take, and you might have a fire hazard. So it's important that we do have loads, and they provide some resistance. And if we want to track this, we can compare the potential difference that we see and the current that's going through the load. In general, every load's resistance is some constant value. It's based on certain internal properties about that thing that's resisting it that determines how much resistance it has. But if we want to be able to calculate its resistance, we can develop a formula called Ohm's law that's based on voltage and current. And what we see is that the resistance that something produces is directly proportional to the voltage drop that we see in a load. So for example, if something is providing a lot of resistance, we will see a very large drop in potential. So that's direct proportionality. When we have large resistance, we have a large drop in potential. But we also see that resistance is inversely proportional to the current, I. Because if something's producing a lot of resistance, it's going to allow only a small amount of current to get through. Or if something has a very low resistance, we'll see a very high amount of current get through. So that's inverse proportionality. And just like we saw when we talked about Newton's second law, we can use those proportionalities to develop an overall statement that says that resistance in general is equal to your voltage divided by your current. R equals V over I. Typically, though, we just rearrange this, similar to what we did with Newton's second law, and we write it more in a multiplicative form, and we call it V equals IR. So V, of course, is still just voltage or potential difference. It's measured in volts, of course. I is the current in amps, and then R is the resistance. And the man who came up with this law, Ohm, named the unit after himself. So we call resistance ohms. And an ohm is really just a volt per amp, because we're taking something in volts and dividing by amps. So it's how many volts of potential difference we see per each amp of current that travels through a certain load. So calculations using this are something you actually probably got a little bit of practice of in grade 9. And you might have forgotten some of those, so it might be useful just to take a few seconds and see if we can solve a basic problem using some of these facts. So if we know a toaster oven uses 9.65 amps of current, and it's plugged into a wall outlet, and wall outlets on average produce a voltage of 120 volts. Let's try and use this to figure out its resistance. So remember, current we use an I to represent, so that's 9.65 amps. Voltage is 120 volts, and we are looking for R, which will be some number of ohms that we'll try and find. So we could use the fact that V is equal to IR, but we can already use it in its form that's already solved for resistance. So resistance, we saw before, is voltage divided by current, V over I. So if we plug in the values that we have, 120 volts divided by 9.65 amps, and of course, again, our unit will technically be volts per amp of current, but a volt per amp is really just an ohm. And so when we do that, we'll get something like 12.435 and some other decimals, which to two significant digits is about 12 ohms. And that symbol for ohms kind of looks like two dancing pairs of feet. And that is really just the Greek letter omega that we use to represent ohms. And from there, it's useful to remember that these loads can be arranged either in a series circuit or possibly in some kind of parallel circuit. And the way that we add together or total up that resistance is different depending on if they're in series or parallel. So when they're just in series, a whole bunch of resistors in a series circuit can be easily found in terms of their total resistance. And all we need to do is just add all of the smaller resistances together. So if we have a bunch of different resistors, and we call them R1, R2, R3, and so on. If we just add all of those individual resistances together, we get the total resistance of the overall series circuit. So that's a pretty straightforward calculation, and so it's not that worthwhile to practice one here. What is a little bit trickier, though, is when we have resistance in a parallel circuit. So if we have several resistors that are connected together but on parallel paths or as part of a parallel circuit, we actually find the resistance in a little bit different way. And what we actually do first is we calculate the reciprocal of the total resistance, or 1 over the total resistance. And to find that reciprocal value, we actually add the reciprocals of each of the separate resistors. And so the sum of all the reciprocal values equals the reciprocal of the total. Now that's a little bit strange mathematically to sort of picture, so this one is really worthwhile if we take a second and go through a full calculation. So for example, let's say we have a parallel circuit and all 4 of the loads are on parallel paths, or paths that are separate from one another, parallel to one another. And we're shown the 4 resistances, and we're just trying to find the total resistance. So we'll write down what we have. We have our first resistor is 4 ohms. Our second resistor is 24 ohms. Our third resistor, you're getting lots of practice writing down the ohm symbol, is 3 ohms. And our fourth resistor is 12 ohms. We are just looking for our, we could call it our tot, or I'm just going to use a T to represent total, RT, total resistance. So, in general, the formula for us will be that 1 over the total resistance, or in other words, remember that just means the reciprocal of the total resistance, is equal to the reciprocal of each resistor added together. And in this case, we have 4 of them. So we'll just write down all 4. And then, of course, in our next step, we'll just plug in the values that we have. So it's really 1 over 4 plus 1 over 24 plus 1 over 3 and 1 over 12. Now, if we had to, we could figure out what all of those fractions are in decimal form, and then just add together all of those decimal numbers. In this case, though, they all happen to be denominators, or fractions, that can easily lead to a common denominator, in this case of 24. So if we rewrite all these fractions with a denominator of 24, what we really have is 6 24ths plus 1 24th, that one already had the correct denominator, plus 8 24ths, plus 2 24ths. When we add all of that together, again, we're just focusing on the addition of the numerators then. On top, that means we get 17, and our denominator is still 24. But that's not the total resistance, remember. What we've actually found is the reciprocal of the total resistance. So in order to actually find the total resistance, we just take the reciprocal of the answer that we got. So we take this fraction of 17 over 24, and if we want to find the reciprocal of this fraction, well, we could do 1 divided by that fraction, but if it's already in a fractional form, an easier way to do that is just to switch the top and the bottom of the fraction. So the reciprocal then, if we're sort of taking the reciprocal of both sides of the equation, that then gets us that the total resistance is actually 24 over 17. And that would actually just be a perfectly correct answer. It's a little strange to leave something in a fractional form, but that actually is the best way you could state your answer, because that gives the exactly correct value. If we were to divide this out, we'd get a decimal number, but then we would have to round that decimal number off somewhere. Whereas this number, this fractional number, actually completely and exactly tells us the total resistance. And of course, don't forget that really that's how many ohms of resistance the total circuit is giving. So knowing Ohm's law and knowing how to calculate total resistances, that gives us some really important tools in our toolbox when we go to eventually try and find unknown values in circuits. But we also need a couple really important laws to back us up when we try and solve different things in circuits. And they were both discovered by a physicist named Kirchhoff. And one is a law that tells us something about voltages, and the other is one that tells us something about currents. And so his voltage law says that the total voltage rise that we see from all the sources in a closed loop, meaning one single path that electrons could follow, that total voltage rise from all the sources must equal the sum of all the voltage drops across all loads within that closed loop. So for example, if something is provided 9 volts of energy from a 9-volt battery, that's how much voltage the source is providing, that's the voltage rise. If we had, let's say, 3 different loads, those 3 different loads would all have to produce voltage drops that also add up to 9 volts. Or you could think of it as negative 9 volts in terms of their voltage drops. So whatever voltage rise is supplied to the circuit must be equaled out by the sum of the voltage drops. In other words, the amount of energy we give to each charge needs to get fully used up by the charges as they flow through that path. But Kirchhoff also has a law about current, because we've also seen that in parallel circuits, there are different paths that current can follow. It doesn't all flow around one specific path. There are different ones. And that's what Kirchhoff's law helps us to understand. And his law for current said that the total current that's entering a node, and a node just means some junction point in a circuit where the current could go in different paths from there, but whatever current is entering that node must be equal to the sum of all currents that are exiting that node. And again, when we just see these things in regular language, they can be a little bit hard to understand, but they'll be a little bit easier to understand when you see them through a specific example. But there are special things that these laws can tell us about how series circuits and parallel circuits will behave in terms of their loads. So for example, it tells us that for each load, the current in a series circuit will remain constant, because a series circuit has only one path for the current to follow. So whatever current value we start with, that same amount of current will travel through the entire circuit. But it means that the potential difference, or the voltage, will get split up. Because if there are multiple loads around the series circuit, they all need to add up back to the original voltage rise. And so whatever amount of voltage is supplied, that will get used up in separate pieces by each of the loads. Or in other words, it'll get split up amongst all of the loads. So that when we put all of those load voltage drops back together, it will equal the original voltage rise. In a parallel circuit, though, strangely, we kind of see the opposite happening. Because in a parallel circuit, the current has different paths that it can follow. So what happens is the current actually gets split up, because some of the current will travel in one path when they get to a certain node, and some will take a different path. So the current will get split up. But for reasons that I'll explain in a bit more detail in class, what we actually notice is that the potential difference might remain constant. So if all the loads are on completely parallel paths to one another, that means when we get a certain amount of voltage supplied from the source, if it only travels through one of those loads in its path, it will use up all of that voltage as it goes through that path. And the same will be true for all loads that are connected in parallel. And again, I'll demonstrate this in a bit more detail in class. So let's take a look at a couple of specific examples of some places where Kirchhoff's laws might help us. So let's say we have a series circuit, and we know that the source has 120 volts being supplied, and we know there's 4 loads with different potential differences. And if we know 3 of those loads, we should be able to figure out the potential difference of the last load. And that's just a little typo in your notes. This shouldn't say last source. We really want to find the last load. That's really what we're looking for. So let's write down some things that we know. Well, we know the original voltage supplied by the source, which I'm going to call Vs, is 120 volts. And then all of the voltage drops, I'm just going to call V1 and V2 and so on. So V1 is what I'll call the 36 volts. V2 will be 28 volts. V3 is 54 volts. But we don't know the 4th one. So that's our required information, is V4. And let's try and write out a mathematical statement that connects what we know about Kirchhoff's law. And his law says that whatever original voltage is supplied by the source, which we call Vs, must be equal to all of the voltage drops added together. And those are what we called V1 and V2 and V3 and V4. But we know that we actually want V4 all by itself. So if I rearrange this, let's say I put V4 all by itself. The only way I could accomplish that is if I took that original source voltage and subtracted the other three, which should make some logical sense that we're going to start with the total that we know and take away all of the ones that we do. But it also makes mathematical sense. That's what we would do mathematically, just to rearrange this formula to get V4 all by itself. But now we just have things that we can plug in. So it's 120 minus 36 minus 28 minus 54. So when we do all that, we are left with just 2 volts. So that means we know that that fourth load must be using up the last 2 volts available. So it's not necessarily that the voltage gets split up evenly amongst all the loads, but it must get split up in a way that uses up the total voltage that was supplied in the first place. And that gives us a nice tool if we need to work backwards like we just did. Now let's see if we can use his law about current to help us with a parallel situation. So let's say in a parallel circuit, we know that the source has 65 amps of current flowing through it. And let's say that there are 3 loads, and the first 2 each use 20 amps. Let's see if we can figure out how much the third one's going to draw. So the current going through the source, which I'm going to call I with a little subscript S, we know that that's the 65 amps. We also know that the 3 loads have various currents going through them, but the first 2, what I'll call I1 and I2, those are both 20 amps. And we are trying to find the current in the third one, I3. So again, what Kirchhoff's law tells us is that whatever original total current we have, so for example, that total current that was going through the source, it must equal all of those separate currents added back together. Because in this parallel circuit, the current is going to split off into 3 different loads. In other words, take 3 different paths. And the current that goes through the first one, the current that goes through the first one, along with the current through the second one and the current through the third one, all added together are going to give us that total original current that was going through the source. But again, it's I3 that I want and not IS. So I actually just need to rearrange. So this is telling me that the third amount of current, I3, is going to be that original amount supplied by the source, take away the other 2. Or in other words, it's 65 minus 20, subtract another 20, and so we get 25 amps left over. So that's telling us that, again, because we know that in 2 of the paths there were 20 amps each of current going through those loads, we must have 25 amps of current that are going through the final load. That's what Kirchhoff's current law can help us to figure out. We can use all of these tools, Kirchhoff's laws and Ohm's law, and what we know about total resistance, to help us solve more complex situations with circuit analysis. And that's what example 5 gets into. So if you really want to push ahead, you can try and solve for some of those unknown values using Ohm's law and Kirchhoff's laws. But we're going to take some time in class and go through this in more detail and see how we can put all of these laws together when we're solving for multiple unknown values.